Vesta, minor planet designation for Vesta, is one of the largest asteroids in the Solar System, with a mean diameter of 525 kilometers. It was discovered by Heinrich Wilhelm Olbers on March 29, 1807 and is named after Vesta, the virgin goddess of home and hearth from Roman mythology. Vesta is the second most massive asteroid after the dwarf planet Ceres, and it comprises an estimated 9% of the mass of the asteroid belt. The less massive Pallas is slightly larger, making Vesta third in volume. Vesta is the last remaining rocky protoplanet of the kind that formed the terrestrial planets. Numerous fragments of Vesta were ejected by collisions 1 and 2 billion years ago that left two enormous craters occupying much of Vesta's southern hemisphere. Debris from these events have fallen to Earth as howardite eucrite diogenite meteorites, which have been a rich source of information about Vesta. Vesta is the brightest asteroid visible from Earth. Its maximum distance from the Sun is slightly farther than the minimum distance of Ceres from the Sun, though its orbit lies entirely within that of Ceres. NASA's Dawn spacecraft entered orbit around Vesta on July 16, 2011 for a one-year exploration and left orbit on September 5, 2012 heading for Ceres. Researchers continue to examine data collected by Dawn for additional insights into the formation and history of Vesta. Dawn data can be accessed by the public at this UCLA website. Discovery. Heinrich Olbers discovered Pallas in 1802, the year after the discovery of Ceres. He proposed that the two objects were the remnants of a destroyed planet. He sent a letter with his proposal to the English astronomer William Herschel, suggesting that a search near the locations where the orbits of Ceres and Pallas intersected might reveal more fragments. These orbital intersections were located in the constellations of Ceres and Virgo. Olbers commenced his search in 1802, and on March 29, 1807 he discovered Vesta in the constellation Virgo. A coincidence, because Ceres, Pallas, and Vesta are not fragments of a larger body. Because the asteroid Juno had been discovered in 1804, this made Vesta the fourth object to be identified in the region that is now known as the asteroid belt. The discovery was announced in a letter addressed to German astronomer Johann H. Schra dated March 31. Because Olbers already had credit for discovering a planet, he gave the honor of naming his new discovery to German mathematician Carl Friedrich Gauss, whose orbital calculations had enabled astronomers to confirm the existence of Ceres, the first asteroid, and who had computed the orbit of the new planet in the remarkably short time of 10 hours. Gauss decided on the Roman virgin goddess of home and hearth, Vesta. Name: Vesta was the fourth asteroid to be discovered, hence the number 4 in its formal designation. The name Vesta, or national variants thereof, is in international use with two exceptions, Greece and China. In Greek the name adopted was the Hellenic equivalent of Vesta, Hestia. In English, that name is used for 46 Hestia. In Chinese, Vesta is called the hearth god, des, star, see paragraph CNEY copyright NXANG, in contrast to the goddess Vesta, who goes by her Latin name. Upon their original discovery, Vesta, Ceres, Pallas, and Juno were classified as planets and each had its own planetary symbol. Vesta was likewise classified as a planet, and along with its name, Gauss designed an appropriate planetary symbol, paragraph, the altar of Vesta with its sacred fire. In Gauss's conception this was drawn. In its modern form it is. After the discovery of Vesta, no further objects were discovered for 38 years, and the Solar System was thought to have 11 planets. However, in 1845 new asteroids started being discovered at a rapid pace, and by 1851 there were 15, each with its own symbol, in addition to the 7 major planets. It soon became clear that it would be impractical to continue inventing new planetary symbols indefinitely, and some of the existing ones proved difficult to draw quickly. That year the problem was addressed by Benjamin Apthorpe Gould, who suggested numbering asteroids in their order of discovery, and placing this number in a disk as the generic symbol of an asteroid. Thus the fourth asteroid, Vesta, acquired the generic symbol £. This was soon coupled with the name into an official number name designation, £. Vesta, as the number of minor planets increased. By 1858, the circle had been simplified to parentheses, and Vesta, which was easier to typeset. Other punctuation such as for, Vesta and for, Vesta was also used, but had more or less completely died out by 1949. Today either Vesta or more commonly for Vesta is used. Early measurements, photometric observations of Vesta were made at the Harvard College Observatory in 1880–1882 and at the Observatoire de Toulouse in 1909. These and other observations allowed the rotation rate of Vesta to be determined by the 1950s. However, the early estimates of the rotation rate came into question because the light curve included variations in both shape and albedo. Early estimates of the diameter of Vesta ranged from 383 to 444 km. E. C. Pickering produced an estimated diameter of 513 plus or minus 17 km in 1879, which is close to the modern value for the mean diameter, but the subsequent estimates ranged from a low of 390 km up to a high of 602 km during the next century. The measured estimates were based on photometry. In 1989, speckle interferometry was used to measure a dimension that varied between 498 and 548 km during the rotational period. In 1991, an occultation of the star SAO 93228 by Vesta was observed from multiple locations in the eastern United States and Canada. Based on observations from 14 different sites, the best fit to the data is an elliptical profile with dimensions of about 550 km, 462 km. Vesta became the first asteroid to have its mass determined. Every 18 years, the asteroid 197 Eucrite approaches within 0.04 AU of Vesta. In 1966, based upon observations of Vesta's gravitational perturbations of Eucrite, Hans G. Hertz estimated the mass of Vesta as a 10 solar masses. More refined estimates followed, and in 2001 the perturbations of 17 Thetis were used to estimate the mass of Vesta as a 10 solar masses. Physical characteristics. Vesta is the second most massive body in the asteroid belt, though only 28% as massive as Ceres. The surface area is approximately the same as that of Pakistan. Vesta orbits in the inner asteroid belt interior to the Kirkwood Gap at 2.50 AU. It has a differentiated interior and is similar to two Pallas in volume but about 25% more massive. Vesta's shape is close to a gravitationally relaxed oblate spheroid, but the large concavity and protrusion at the southern pole combined with a mass less than 5 10–20 kg precluded Vesta from automatically being considered a dwarf planet under International Astronomical Union Resolution XXVI5. A recent analysis of Vesta's shape and gravity field using data gathered by the Dawn has shown that Vesta is currently not in hydrostatic equilibrium. Its rotation is relatively fast for an asteroid in prograde, with the North Pole pointing in the direction of right ascension 20 hearth 32 min, declination plus 48 degree with an uncertainty of about 10 degree. This gives an axial tilt of 29 degree. Temperatures on the surface have been estimated to lie between about a 20 degree Celsius with the Sun overhead, dropping to about a 190 degree Celsius at the winter pole. Typical daytime and nighttime temperatures are a 60 degree Celsius and a 130 degree Celsius respectively. This estimate is for May 6, 1996, very close to perihelion, although details vary somewhat with the seasons. Surface features. Prior to the arrival of the Dawn spacecraft, some Vestan surface features had already been resolved using the Hubble Space Telescope and ground-based telescopes. The arrival of Dawn in July 2011 revealed in detail the complex surface of Vesta, Rhea Silvia and Venus craters. The most prominent of these surface features are two enormous craters, the 500-kilometer-wide Rhea Silvia crater, centered near the South Pole, and the 400-kilometers-wide Venus crater. The Rhea Silvia crater is younger and oval as the Venus crater. The Dawn science team named the younger, more prominent crater Rhea Silvia, after the mother of Romulus and Remus and a mythical Vestal Virgin. Its width is 95% of the mean diameter of Vesta. The crater is about 19 kilometers deep. A central peak rises 23 km above the lowest measured part of the crater floor, and the highest measured part of the crater rim is 31 km above the crater floor low point. It is estimated that the impact responsible excavated about 1% of the volume of Vesta, and it is likely that the Vesta family and V-type asteroids are the products of this collision. If this is the case, then the fact that 10-kilometer fragments have survived bombardment until the present indicates that the crater is at most only about 1 billion years old. It would also be the site of origin of the head meteorites. All the known V-type asteroids taken together account for only about 6% of the ejected volume, with the rest presumably either in small fragments, ejected by approaching the 3-1 Kirkwood gap, or perturbed away by the Yarkovsky effect or radiation pressure. Spectroscopic analyses of the Hubble images have shown that this crater has penetrated deep through several distinct layers of the crust, and possibly into the mantle, as indicated by spectral signatures of olivine. The large peak at the center of Ria Silvia is 20 to 25 kilometers high and 180 kilometers wide. Other craters. Several old, degraded craters rival Ria Silvia and Venera in size, though none are quite so large. They include Feralia planitia, shown at right, which is 270 km across. More recent, sharper craters range up to 158 km Varanilla and 196 km Postumia. Snowman Craters. The Snowman Craters is an informal name given to a group of 3 adjacent craters in Vesta's northern hemisphere. Their official names from largest to smallest are Marcia, Calpurnia and Minutia. Marcia is the youngest and crosscuts Calpurnia. Minutia is the oldest. Troughs. The majority of the equatorial region of Vesta is sculpted by a series of concentric troughs. The largest is named Devaglia Fossa. Despite the fact that Vesta is a 1/7 the size of the Moon, Devaglia Fossa dwarfs the Grand Canyon. A second series, inclined to the equator, is found further north. The largest of the northern troughs is named Saturnalia Fossa. These troughs are thought to be large-scale graben resulting from the impacts that created Ria Silvia and Venera craters, respectively. They are some of the longest chasms in the Solar System, nearly as long as Ithaca Chasma on Tethys. The troughs may be graben that formed after another asteroid collided with Vesta, a process that can happen only in a body that, like Vesta, is differentiated. Vesta unregistered trademark S differentiation is one of the reasons why scientists consider it a protoplanet. Surface composition, compositional information from the visible and infrared spectrometer, gamma-ray and neutron detector, and framing camera, all indicate that the majority of the surface composition of Vesta is consistent with the composition of the howardite, eucrite, and diogenite meteorites. The Ria Silvia region is richest in diogenite, consistent with the Ria Silvia forming impact excavating material from deeper within Vesta. The presence of olivine within the Ria Silvia region would also be consistent with excavation of mantle material. However, olivine has only been detected in localized regions of the northern hemisphere, not within Ria Silvia. The origin of this olivine is currently uncertain. Features associated with volatiles. Pitted terrain has been observed in 4 craters on Vesta, Marcia, Cornelia, Numizia and Licinia. The formation of the pitted terrain is proposed to be degassing of impact-heated volatile-bearing material. Along with the pitted terrain, curvilinear gullies are found in Marcia and Cornelia craters. The curvilinear gullies end in lobate deposits, which are sometimes covered by pitted terrain, and are proposed to form by the transient flow of liquid water. Hydrated materials have also been detected, many of which are associated with areas of dark material. Consequently, dark material is thought to be largely composed of carbonaceous chondrite, which was deposited on the surface by impacts. Carbonaceous chondrites are comparatively rich in mineralogically bound OH. Geology. There is a large collection of potential samples from Vesta accessible to scientists, in the form of over 1,200 ahead meteorites, giving insight into Vesta's geologic history and structure. NASA Infrared Telescope Facility studies of asteroid 1999 TA-10 suggest that it originated from deeper within Vesta than the head meteorites. Vesta is thought to consist of a metallic iron nickel core 214 226 km in diameter, an overlying rocky olivine mantle, with a surface crust. From the first appearance of core rich inclusions, a likely timeline is as follows. Vesta is the only known intact asteroid that has been resurfaced in this manner. Because of this, some scientists refer to Vesta as a protoplanet. However, the presence of iron meteorites and dendritic meteorite classes without identified parent bodies indicates that there once were other differentiated planetesimals with igneous histories, which have since been shattered by impacts. On the basis of the sizes of V-type asteroids, and the depth of Regolith crater, the crust is thought to be roughly 10 kilometers thick. Findings from the NASA Dawn spacecraft have found evidence that the troughs that wrap around Vesta could be graben formed by impact-induced faulting, meaning that Vesta has more complex geology than other asteroids. Vesta could have been classified as a dwarf planet if it had retained a spherical shape, and it has other qualities that lead to the belief it could be a protoplanet. The only thing that knocked it out of the category of a dwarf planet was the formation of two large impact basins at its southern pole. At the time of these impacts, Vesta was not warm and plastic enough to return to a shape in hydrostatic equilibrium. Regolith, Vesta's surface is covered by regolith distinct from that found on the Moon or asteroids such as Itokawa. This is because space weathering acts differently. Vesta's surface shows no significant trace of nanophase iron because the impact speeds on Vesta are too low to make rock melting and vaporization an appreciable process. Instead, regolith evolution is dominated by brecciation and subsequent mixing of bright and dark components. The dark component is probably due to the infall of carbonaceous material, whereas the bright component is the original Vesta basaltic soil. Fragments. Some small solar system bodies are believed to be fragments of Vesta caused by collisions. The Vestian asteroids and head meteorites are examples. The V-type asteroid 1929 Collar has been determined to have a composition akin to cumulate eucrite meteorites, indicating its origin deep within Vesta's crust. Vesta is currently one of only 6 identified solar system bodies for which we have physical samples, coming from a number of meteorites believed to be Vestan fragments. The other identified solar system samples are from Earth itself, meteorites from Mars, and samples returned from the Moon, the comet Wall-2, and the asteroid 25143 Itokawa. Exploration. In 1981, a proposal for an asteroid mission was submitted to the European Space Agency. Named the Asteroidal Gravity Optical and Radar Analysis, this spacecraft was to launch sometime in 1990–1994 and perform 2 flybys of large asteroids. The preferred target for this mission was Vesta. Agera would reach the asteroid belt either by a gravitational slingshot trajectory past Mars or by means of a small ion engine. However, the proposal was refused by the ESA. A joint NASA–ESA asteroid mission was then drawn up for a multiple asteroid orbiter with solar electric propulsion, with one of the mission profiles including an orbit of Vesta. NASA indicated they were not interested in an asteroid mission. Instead, the ESA set up a technological study of a spacecraft with an ion drive. Other missions to the asteroid belt were proposed in the 1980s by France, Germany, Italy and the United States, but none were approved. Exploration of Vesta by flyby and impacting penetrator was the second main target of the first plan of the multi-IM Soviet Vesta mission, developed in cooperation with European countries for realization in 1991–1994 but cancelled due to the Soviet Union disbanding. In the early 1990s, NASA initiated the Discovery Program, which was intended to be a series of low-cost scientific missions. In 1996, the program's study team recommended as a high-priority a mission to explore the asteroid belt using a spacecraft with an ion engine. Funding for this program remained problematic for several years, but by 2004 the Dawn vehicle had passed its critical design review. It launched on September 27, 2007, as the first space mission to Vesta. On May 3, 2011, Dawn acquired its first targeting image 1.2 million kilometers from Vesta. On July 16, 2011, NASA confirmed that it received telemetry from Dawn indicating that the spacecraft successfully entered Vesta's orbit. It was scheduled to orbit Vesta for 1 year, until July 2012. Dawn's arrival coincided with late summer in the southern hemisphere of Vesta, with the large crater at Vesta's south pole in sunlight. Because a season on Vesta lasts 11 months, the northern hemisphere, including anticipated compression fractures opposite the crater, would become visible to Dawn's cameras before it left orbit. Dawn left orbit around Vesta on September 4, 2012 11:26 p.m. PDT to travel to Ceres. NASA DLR released imagery and summary information from a survey orbit, 2 high-altitude orbits and a low-altitude mapping orbit, including digital terrain models, videos and atlases. Scientists also used Dawn to calculate Vesta's precise mass and gravity field. The subsequent determination of the J2 component yielded a core diameter estimate of about 220 km, assuming a crustal density similar to that of the head. Observations from Earth orbit. Observations from Dawn. Vesta comes into view as the Dawn spacecraft approaches and enters orbit. Detailed images retrieved during the high-altitude and low-altitude mapping orbits are available on the Dawn mission website of JPL NASA. Coordinate systems. There are 2 longitudinal coordinate systems in use for Vesta, with prime meridians separated by 150 degree. The IAU established a coordinate system in 1997 based on Hubble photos, with the prime meridian running through the center of Olbers Regio, a dark feature 200 km across. When Dawn arrived at Vesta, mission scientists found that the location of the pole assumed by the IAU was off by 10 degree, so that the IAU coordinate system drifted across the surface of Vesta at 0.06 degree per year, and also that Olbers Regio was not discernible from up close, and so was not adequate to define the prime meridian with the precision they needed. They corrected the pole, but also established a new prime meridian 4 degree from the center of Claudia, a sharply defined crater 700 meters across, which they say results in a more logical set of mapping quadrangles. All NASA publications, including images and maps of Vesta, use the Claudian meridian, which is unacceptable to the IAU. The IAU Working Group on Cartographic Coordinates and Rotational Elements recommended a coordinate system, correcting the pole but rotating the Claudian longitude by 150 degree to coincide with Olbers Regio. It was accepted by the IAU, though it disrupts the maps prepared by the Dawn team, which had been positioned so they would not bisect any major surface features. Visibility. Its size and unusually bright surface make Vesta the brightest asteroid, and it is occasionally visible to the naked eye from dark skies. In May and June 2007, Vesta reached a peak magnitude of +5.4, the brightest since 1989. At that time, opposition and perihelion were only a few weeks apart. Less favorable oppositions during late autumn 2008 in the northern hemisphere still had Vesta at a magnitude of from +6.5 to +7.3. Even when in conjunction with the Sun, Vesta will have a magnitude around +8.5. Thus from a pollution-free sky it can be observed with binoculars even at elongations much smaller than near opposition. 2010–2011. In 2010, Vesta reached opposition in the constellation of Leo on the night of 17 February 18, at about magnitude 6.1, a brightness that makes it visible in binocular range but not for the naked eye. Under perfect dark sky conditions where all light pollution is absent, it might be visible to an experienced observer without the use of a telescope or binoculars. Vesta came to opposition again on August 5, 2011, in the constellation of Capricornus at about magnitude 5.6. 2012–2013, Vesta was at opposition again on Sunday 9 December 2012. According to Sky and Telescope magazine, this year Vesta will come within about 6 degrees of 1 Ceres during the winter of 2012 and spring 2013. Vesta orbits the Sun in 3.63 years and Ceres in 4.6 years, so every 17 years Vesta overtakes Ceres. On December 1, 2012, Vesta had a magnitude of 6.6, but decreasing to 8.4 by May 1, 2013. 2014, Ceres and Vesta should come within 1 degree of each other in the night sky in July 2014. See also, 3103 Edger, 3551 Varinia, 3908 Nix, 4055 Magellan, Asteroids in Fiction, Diogenite, Eucrite, Howardite, Vesta family, list of tallest mountains in the Solar System. Notes: Mark Raymond of the JPL Dawn team used Vestian a few times in 2010 and early 2011 in his Dawn journal. However, since that time, and outside the journal, the form Vestan has been used by JPL. Most modern print sources also use Vestan, though the Planetary Society continues to use Vestian. The form Vestalian correctly refers to people or things associated with Vesta, such as the Vestal Virgins, not to Vesta herself. On February 10, 2009, during Ceres perihelion, Ceres was closer to the Sun than Vesta, because Vesta has an aphelion distance greater than Ceres's perihelion distance. See paragraph or copyright ISA TC, with an obscura, is the closest Chinese approximation of the Latin pronunciation Vesta. Other sources contemporaneous to Gauss used a more elaborate form of this symbol. Or Venezuela or Tanzania. Somewhat larger than Texas and Tenor, the UK. That is, blue in the north does not mean the same thing as blue in the south. Note that there is very strong evidence that 6 Hebe is the parent body for H. chondrites, one of the most common meteorite types. References. General references. External links. JPL Ephemeris, NASA's Dawn spacecraft, NASA video clips of Vesta rotating in color, views of the Solar System, Vesta, Hubble site, Hubble maps the asteroid Vesta, Encyclopaedia Britannica, Vesta full article, Hubble site, Hubble reveals huge crater on the surface of the asteroid Vesta, Hubble site, short movie composed from Hubble Space Telescope images from November 1994. Adaptive optics views of Vesta from Keck Observatory, differentiated interior of Vesta, Vesta image gallery at Wikimedia Commons, 4 Vesta images at ESA Hubble, Hubble views of Vesta on the Planetary Society weblog, Dawn at Vesta, NASA video, Vesta nomenclature and Vesta map with feature names from the USGS planetary nomenclature page, Vesta Atlas, Vesta to scale, 2, 3D shape model of Vesta, Vesta in attempted natural color, PDS small bodies image browser, DLR public Dawn product site.